Hey everyone, thanks so much for coming. So as our moderator presented me, I'm really passionate about linguistics, and I work as a computational linguist. I have like 7 years of experience working in computational linguistics, and I want to talk today about feature engineering, about structural linguistics, about how you can utilize this knowledge of linguistics when you're doing machine learning, when you're solving natural language processing tasks. And we will be talking about lexical simplification, and that's kind of the topic of my presentation. Was supposed to be a pun or something. So specifically about the lexical simplification. First, I'll give you some motivation about text simplification in general and the position of lexical simplification in the task of text simplification. Then we'll build a baseline. We'll choose an approach and build a baseline for that, and then we'll discuss like 2 different components of lexical simplifications further on. So first of all, like a very simple question: where do complex words come from? And a very simple answer to that: they come from complex texts, right? So the question now is, what are complex texts? So the texts that can be complex, these can be texts that are written in certain area, and we as non-specialists in that area can have a hard time understanding, like technical texts, like medical texts, like legal language, and so on. And there are many tools that aim to do text simplification for example, legal language for everybody to understand, for non-specialists to understand. Or, for example, this can be average level English texts that can be hard to understand for second language learners, or people with reading impairments, or children, right, different age groups, or native speakers with low literacy level. And text simplification tools can help writers, bloggers, journalists, and so on to appeal to a larger audience, right? Or if you're like anything like me or my friend Joey here, and you have to write something really important, like a letter to a baby adoption agency to support, your friends, and you want to sound really smart, simple sentences like "they are warm, nice people with big hearts," when you overuse a thesaurus or a dictionary in the language that you want to write in, your sentence becomes something like "they are humid, prepossessing Homo sapiens with full-sized aortic pumps," which doesn't make any sense, right? So text simplification can help you bring that back. So the task of text simplification in NLP is to facilitate reading comprehension for different groups of people, for non-specialists, for second language learners, for children, or even it can simplify stuff for other NLP applications. Think about text summarization. It's easier to do text summarization if your original text is already simpler. Or it can facilitate machine translation, or it can facilitate information extraction and information retrieval. So like many kinds of ways to use text simplification in real life. There are different ways of text simplification. The main ones are syntactic simplification, lexical, and explanation generation. If we're talking about syntactic simplification, we take like really long, complex sentences, like London, where we are now, thanks for coming, which is the capital of the United Kingdom, is located in southeastern England. And you can break that complex sentence into 2 shorter ones, and that will facilitate reading comprehension of people with lower literacy level, for example. Lexical simplification is simplifying lexicon, simplifying the words or short phrases that you use, also eliminating like jargon or eliminating slang or outdated terms, neologisms, and so on and so forth. So this relates to what our friend Joey wrote earlier today. And this is the kind of text simplification that we are going to talk to the end of the presentation today. And explanation generation, since I mentioned that too, is actually simplifying text by making it longer, by enriching it with the information that wasn't there. Like if you say the baby was born with pulmonary atresia, like how many people know what pulmonary atresia is, right? So when you want to simplify the text, you would add an explanation of what pulmonary atresia is, and your simplified text will actually be longer than the original text. But we are talking about lexical simplification today, so how to make words simpler. You won't find many demos of lexical simplifications on the web because this is still an unsolved task. And the last share task, which we'll also mention later, just happened, this summer. I'll mention that later. Sorry. So one of the stuff that you can find, one of the examples that you can find on the web is IBM Content Clarifier, and you can see an original piece of text and a simplified piece of text here, and you can see that such words as humongous or super annotated are replaced by words like large and old, which are more familiar to a broader audience. We at Grammarly, so I work at Grammarly, also had to work on text simplification at a certain point, and for us it was more like Joey's example. So a person is writing something important, they don't know the word, they go to the dictionary, they pick like the smartest word that they can find in this dictionary, and they put it in the context, and instead of sounding smart, they can sound like either stupid or they can just harm the comprehension of the text that they are writing for their audience. So this is like the example of what Grammarly is doing. So this was the motivation, and I hope that I gave you enough reason to believe that this task is important now. Let's see how we can approach it. What we already know, there were 2 shared tasks on complex word identification. So not even simplification, but just how to identify complex words in the text. The one took place in 2016, and they released a data set which was of very bad quality. So they annotated some Wikipedia and news articles with Amazon Mechanical Turk, and Turkers were supposed to mark some words as complex or non-complex. But if you look closely at that data set, you would see that words like one or laughter were marked as complex, which doesn't help the task. And with some sentences, it looked like the annotation was just random, because like in the 3rd sentence that you can see on the slide, like every other word is just marked as complex, which also doesn't help. Another task, shared task, took place this year, and the data was like a little bit better, but not that much. So we have a problem with data apparently. What we learned from this shared task is that first, a separate complex words identification module helps build the complex word simplification system, the lexical simplification system. So we would want to have like 2 separate modules for probably. The second thing that we learned is that traditional machine learning outperforms deep learning for complex word identification. And the highest performance on complex word identification with traditional machine learning, with like linear regression for probabilistic complex word identification or like random forest, achieved 81, 82 using F1, like F1 measure, but deep learning methods didn't rank that high. But this gives us opportunity to do some cool feature generation today, right? And talk about that. And some non-annotated data that we can use to test our hypothesis and so on are Wikipedia and simple Wikipedia. I don't know if you know, guys, but there's a separate Wikipedia written in simple English that like people of that children can read, or non-specialists can read, or non-native speakers can read with much greater ease. And also there are some news resources like Newsella that I linked here too, that allow the same piece of news at different levels of readability, so that people, again, with different levels of reading comprehension can get the same piece of information. So what that gives us, I showed you the data. Let's build the pipeline. So we have our raw text. We will have to do some text processing, like we will have to detect that the text is written in English, for example, if we have multiple sources of text. That means language filter here. We will have to tokenize this text to break this text into separate tokens, because we're going to work with words, right? Then we will do some part of speech tagging. This is a very common piece of NLP pipeline that is usually used, and we will use parts of speech also as feature in our module later. And after this text processing, we can do some feature extraction. And if we use like our intuition or in any paper that we find in complex words, we can see that the main 3 features are the word length, word frequency, and part of speech. So we just assume that complex words are long and have low frequency and rarely used in the language, right? So that sounds like really obvious. And that will help us build our complex word identification module, which will be like a classifier, for example, linear regression probabilistic classifier. That will give us potentially complex words. Now we will be able to use some kind of a thesaurus. So a thesaurus is a dictionary that provides synonyms, right, for our words. So we can extract synonyms, a list of synonyms for our words. We can use the part of speech, because for different parts of speech, the word will have different synonyms, right? So that's why we need part of speech tagger too. And then the last thing that we can do is re-rank these synonyms by frequency, right? And just pick the most frequent one, put it back in the text, and voila, we simplify the text. Yeah. So this will be like our baseline. Okay. How will we measure success on our on this complex word identification task that we are building, complex word simplification task that we are building? So any NLP researcher, and I guess like any researcher in the room here, will point out like the first two criteria. First of all, it has to have like good F measure, right? On my test set, of course, and the speed should also be okay. But there's one problem, like. Yeah, we'll say that it's good enough. But there's one problem. We are not the final consumers of applications that we build. So this is what usually happens. Sometimes we are, but in most of the cases, we build these applications for somebody else. So maybe we should probably ask that somebody else what they want our application to be like. And if we ask like real users of these text simplification tools, they will give us the whole list of criteria. Because first of all, they want the tool to simplify the text consistently. And I'll show you a couple of examples on when building this application, you can be very inconsistent. Second of all, they want their text to be still grammatically correct after you simplified it. Second of all, they want your text to be indeed simpler, because sometimes if you just pull another synonym, you're just paraphrasing, but you're not making it simpler. But they don't want you to make their text oversimplified, because making your text too simple can also be a problem. And then the meaning shouldn't change. So there's the whole list of criteria that didn't fit into, like our list. So the regular user will tell you like, no, not good enough. So let's think how we can make it better. And the next section will be, so the next two sections will be on first complex word identification and how to make it better, and then on actually replacing this word with the synonyms and how to make that better. So the first feature, if you remember, that we mentioned was word frequency. How do we calculate word frequency? Well, we just take a large corpus, like say the internet. There's the corpus of an internet language that is called Common Crawl, that lies on Amazon servers that anyone can access, anyone can use. So you just take a large corpus of the English language, say, you tokenize it, and you just count, right? So how difficult can that be? But if you do that, you will find that you don't meet the first criterion that your users want from you, because the first criterion is for your program to be consistent. But it turns out that your program starts marking the word accessorize as simple, but the word accessorizes as complex. Why is that? Because you were counting word forms, not words. The frequencies of word forms, not the frequencies of words, right? If you ask a linguist what a word is, the linguist will tell you that a word is the unity of all of its grammatical forms. So it means that to make your program work consistently, the word frequency of accessorizes should be the same as the word frequency of accessorize, and it actually should be the sum of all of the word forms of this particular word. And if you know, like in British English, this word is spelled a little bit differently, right? Who knows how? So it has an S, right? Not a Z there. So it may sound surprising to you since we're in the United Kingdom today, but internet is very highly biased towards American English. And your program will start marking the word accessorize written with an S as complex, but accessorize written with a Z was as simple, just because their frequency is different on the internet. So actually, the frequency of this word should be the sum of all of these word forms with different spellings. So your program that will make your program, your model more consistent. How do we know like what forms each word has, right? So I wrote out all forms of the word accessorize, but you cannot write out everything, in hand for all the words in the English. So there's a study in linguistics that is called inflectional morphology that explains how grammatical forms of different words in different languages are formed. And first of all, there are like loads of books on this. And second of all, there are loads of resources. So you take a resource that, like Wiktionary. Wiktionary is an online dictionary that is written by people, that is crowdsourced. And Wiktionary has like more than 30 languages, and it has information on inflectional morphology of every word in every language that it encounters, because people, edit it. And you can actually scrape Wiktionary and you have a dictionary with all of the word forms for every word that you need in your language. If we dive deeper into inflectional morphology, for each row, of these grammatical forms, one of the forms is always chosen as a lemma. And that gives us again, a tool or a process that is called lemmatization. And lemmatization is transforming a word from any of its forms, any of its grammatical forms, to its base form, the one that was chosen as base for this particular language. So lemmatization is something that we will need later, because if we want to make a lookup in the dictionaries, words are usually in their base form. So you have to transform from your word accessorizes to its lemma accessorize, and then look for synonyms if you were to do that, for example. All right, moving on. So our second feature actually triggers the same problem as our first feature. If we just look at word length, it turns out that your program will mark the word friend as simple, but then the word friendliness as complex. But you don't want that, because any person who already learned the word friend will understand the word friendliness. You don't want the word friendliness to be marked as complex. But it's so much longer, right? And we're using word length as a feature. So why isn't the word friendliness complex? It turns out that some long words are actually simple because you can easily derive like the components that they were built from, right? So if you say mistreatment, right, you know that it comes from the word treat. If you know the word treat, you know the word mistreatment. If you know the word mouth and the word water, then you would understand the word mouth watering, and so on. So how do we know, what do we do now, right? So the hypothesis is that if you can get, this original word where your word that you're working with came from, and this original word will be called in linguistics etymon, you will be able to collect the same features for this particular word. So you will be collecting features for the word treat, not for the word mistreatment, but or for both of them, and that will help make your program more accurate and more consistent. So there's another study in linguistics that is called derivational morphology that explains you how words are formed from other words and from other inflections. So the word denationalization here, you can see that it's combined out of 5 different elements, and these elements in linguistics are called morphemes. And you can actually build a tool that is called morphological analyzer that will perform this kind of breakdown for every word in your language that is needed. So in order to build this tool, you can either do a rule-based approach, which is frequently done, or you can do a sequence labeling model that will just mark the levels of the boundaries of morphemes, for example, in your words. And if you do that, you have your original word, you have the word that your word came from, and you can now count frequencies, and you can count word length for both of them. All right, let's move on. What if we go a level lower? What if we go a level lower from the word level, and we will go to the character level? We can formulate it. If we look closely at our complex words, we can see that they have rare letter combinations. And you can build something that we call character n-grams. So n-grams are sequences of elements. In this case, you can also see that I put a caret at the beginning and a $. At the end. This marks the boundaries of the word. This is the beginning of the word, and this is the end of the word. And you can collect different lengths of sequences of characters on this from the word. How does this help us? Just think, let's do, like comparison. So this is the word abhorrence, which is a complex one, and its simpler counterpart, anger. So how many words do you know that start with ABH? Or have something like ABHO in them, right? Not many. But if you look at the word anger and n-grams, character n-grams that we got from it, you can think of words like danger or hunger or like range and so on. So there are many words that are much simpler that use the same character combinations. So character n-grams, like 5 grams are probably an overkill here, but like 3 grams and 4 grams are quite a useful feature in complex word identification. Okay, let's go another level lower. So what's another level lower? So we have a word, then we have characters, then we have sounds, of course. So let's go look at phonetics. If you look closely at complex words, it turns out that they have higher consonant-vowel ratio, right? So here on the slide, you see 2 complex words, procrastinate and flabbergasted, and 2 simpler words, neighborhood. Oh, sorry, I don't know what happened.
Yeah, so all of them are long, right? But neighborhood and information are so much simpler than procrastinate and flabbergasted. If we look at the dictionary of transcriptions, we will find that in simple words, the number of consonants and number of vowels is on average the same. But in complex words, we have so much more consonants than vowels. So, and sometimes the ratio is even 1 to 2. Or 2 to 1, yeah. Okay, what if we go a level higher than the word, right? So we can list like a couple of phonetic features that we can draw from transcription. In addition to ratio of consonants to vowels, we can also have just a number of vowels and consonants, and number of repeating sounds would also be interesting, and number of syllables could either substitute the word length or be used in addition to word length, and so on. Okay, so now let's go a level higher. Let's talk semantics. So semantics is the study of linguistics that talks about meaning, right? So what can you see in the picture? A mouse, right? And how many meanings does the word mouse have? At least 2, right? Okay, the ones that you can see in the picture. So the hypothesis is that complex words have fewer meanings than simpler words. Because simpler words, you use them in everyday language, and they evolve, and their meanings evolve, and they get more and more meanings all the time. But the complex words, you don't use them so frequently, and since you don't use them so frequently, they don't acquire these new meanings. So if you look at any dictionary, or like I did in the WordNet, so WordNet is an open source ontology, which I will also explain in the slide later. It will show you that the simple words like report or mouse have like a lot of meanings. So like mouse has 4 meanings as a noun and 2 meanings as a verb. And now all of you are probably guessing like what other 2 meanings of the word mouse are there, right? Yeah, okay, you'll have to look it up. Or I can tell you after the presentation. But if you look at complex words like elucidate or moribund or abhorrence that we discussed 2 slides ago, you will see that they have like 1 to 2 meanings maximum, sometimes 3, but this will be it. So this is one thing, one feature that we can use from the field of semantics, the number of senses that the word has. How about like other lexical semantic relations between words? So let's have a closer look at WordNet that I mentioned here. So WordNet is an ontology that was built by psycholinguists in Princeton. And this ontology actually contains relations between different meanings in the language. So if we take the word mouse, and 2 meanings of the word mouse, not 4, right? Here we take only 2, that we just mentioned. The word mouse in the meaning of an animal will have a higher level relation that is called hypernym to the word rodent, right? But then it will also have hyponym, the lower level relations, this is a type of. So house mouse, field mouse, and wood mouse are all types of mouse, and mouse is a type of rodent, right? So we have all of these lexical semantic relations between different words or concepts in this that are already written in WordNet and were written by psycholinguists in WordNet like a long time ago. And mouse would also have some sister terms like hamster or rat. But if we look at mouse as electronic devices, so mouse won't have any types here in the WordNet. I guess there weren't many mouses when they did the WordNet there. But it will contain another lexical semantic relation that is called meronym. So meronym is a part of. So a mouse button is, for example, a part of a mouse. What does this tell us? So if we look at a word in this WordNet hierarchy, it will tell us, how many levels are there above this word and how many levels are below this word and how complex is this word, this term, this object or this notion that we are discussing that is represented by this word in this hierarchy, in this WordNet hierarchy. And so as semantic features, we can use the number of senses, which will be like one of the number of meanings, right? Which will be one of the most important features, I guess. And also the number of hypernyms, so number of higher level terms that are above our word. Number of hyponyms, these are like how many types of this object are there, like house mouse, field mouse, and so on. Meronyms and holonyms are also, so meronym is a part of, and holonym is being a part, is a part. Okay, moving on. We can also move like another level higher after semantics. So after semantics, there is another level that is called psycholinguistics. So psycholinguistics is another part of linguistics that, studies our cognitive processes that are related to language comprehension and language production. There's a psycholinguistic database, for example, that we can use that describes how concrete are terms that describe imagibility of different terms. What is imagibility? So imagibility tells you how readily your brain produces images for a certain term. And there are like 9,000 nouns in this database ranked by imagibility. Like if I say the word accident, then the word accident can revive some images in your brain. But if I say the word advantage, like can anyone create an image for advantage? Right, that would be more, so the word advantage has a lower level of imagibility than the word accident, for example, in this database. Yeah, the familiarity, like how many people of certain origin, of certain age know this term, you know, on average. Age of acquisition, like at which age do you start using this word actively, or at which age you passively learn about this word, and so on. So there are a lot of like lexical resources, psycholinguistic resources also that you can use, and you can use this as features in building your complex words identification module. Okay. So now this whole list of features that we just mentioned, that we just listed, will give us will build a good foundation for us to do complex words identification. So now we identified our complex words in the text, in the sentence, or where we are doing that. Now we have to simplify them somehow, right? So how do we do that? So we lemmatize the word, you already know that. We detect the part of speech for this word, because like the word mouse as a noun will have different synonyms than the word mouse as a verb, for example, and so on. There's another step that is skipped here because I won't have time to explain it during this presentation, but we can also do word sense disambiguation. So as I mentioned, like the word mouse has 4 different meanings, and for each of these different meanings, this word will have a different set of synonyms. And you would want to know which set of synonyms to pick. So for simplicity, we won't be discussing this particular step because this is like another an hour and a half lecture on that topic. And for simplicity, we will just decide that our re-ranking algorithm that we will build later today will just pick we'll just put all of the synonyms from all of the senses together, and our re-ranking algorithm will pick the one that is most fitting in this sense. Then we will extract these synonyms from a thesaurus. We will put synonyms in the place of an original word, and we will talk about like how to re-rank them. So we can use a resource that is like thesaurus.com, for example. This is an open thesaurus where you can put your word, like dipsomania, that's a complex word, and it will give you a ton of different synonyms. Then we can put these synonyms in our sentence, right? And the last thing to do would be probably to just re-rank them. But wait, right? If you look closer here, you will see that some of the synonyms, like inebriacy, are actually not simpler than dipsomania. If you change dipsomania to inebriacy, your user won't be very happy. Some other synonyms, like habit here, are too broad, right? If you just change dipsomania to habit, like what kind of habit? Like, is he smoking? Is this a drug abuse, or like what kind of habit? Or is it just bad habit? So you don't want your synonyms to be too broad either. So if we go back to the criteria that we had from our users, right? So our user want the term first to be simpler. How can we define that the term is simpler? Well, we built our complex word identification module, right? So we can use our for example, linear regression model to give probabilities that each of the synonyms is complex, and then we can just filter out the synonyms that are more complex or close to like ours, right? So that's why we built this complex word identification module too. How do we check that the word is not too simple? So there isn't much in the literature, so you can use some heuristics. Like we can check whether the word is not too polysemous, because if word has too many meanings, like habit has at least 6 nominal meanings, at least 6 meanings as a noun. So this may be like too broad word, or words like run, or had. The word like run or had, they have like 30 or more meanings. So if you're replacing a word that has 1 meaning with a word that has 30 meanings, you're definitely oversimplifying the text, or you're even risking to make the text like really ambiguous, like here, that we're not specifying what kind of habit it is. You can also check like how much more frequent this word, this candidate synonym is, because if the gap is too large, then again, you may be changing the meaning too much. Then the question still stays, is it grammatically correct? Like the synonym that we put there, does it keep the sentence grammatically correct? Because this was also one of the criteria that our users wanted. So in this case, for example, everything looks good. You just replace your word with synonyms and that's it. So let's look at other cases. If we have a verb, so verbs, you have different grammatical forms, you already know that. So you would want to first put each of your candidate synonyms in that correct form. Because afterwards, we will be re-ranking the synonyms. We will be re-ranking the sentences together with synonyms, defining which sentence is the most probable, right? And if you make the sentence grammatically incorrect, this will just lower the probability of the sentence and you will just harm your algorithm. Some other examples of grammaticality, right? You would have to look at the correct noun number, or maybe if you have an indefinite article before the word that you are changing, and you have to change it with it, right? If you don't change the indefinite article, the text will become grammatically incorrect, and that will also harm your ranking algorithm. Or if you're working on adjectives, right? You want to change destitute to poor, then you will make more poor, but actually the correct form would be poorer, because in the English language there are very strict rules on when to use more most. This will be like a synthetic way to build degrees of comparison, and when you want to use inflection, this will be analytic, and that's syntactic ways to create degrees of comparison, and so on. So maybe you need to grab another word together with the complex word that you are changing. Or there's also such a phenomenon in linguistics that is called governing. This is how words interact with each other. This is how words collocate with each other. This is how words depend on each other, and so on. So if we have a complex word like collude, and collude can govern the preposition with, or can govern the preposition in. When we change it to conspire, we have to make sure that conspire governs the same prepositions. So in the first case, it will be grammatically correct because conspire also governs the preposition with. In the second case, it will be not grammatically correct because you cannot say conspire in something. So you will have to make sure to either adjust the preposition or to paraphrase it in some way, or to just remove these ungrammatical candidates at all. Okay. So now we took our what we did. We did a lookup to a thesaurus. We took out the list of synonyms. We filtered out the ones that were either too complex, either too simple, or ungrammatical. Yeah. What we do now? So now we want to re-rank these suggestions. And we are going to do that with a language model. Say we have an original sentence, then we have a list of replacements. And for moribund, for example, we can find synonyms like dying, fading, and declining, which doesn't really fit the context, right? Because it's a bit different meaning, and the patient cannot decline, and so on. So we want, for example, our first replacement with dying to be ranked first, right? But we have the whole list of them. We have to re-rank them somehow. And here for simplicity, we will think that we don't need any word sense disambiguation model, because the language model that we're going to build and that will re-rank the synonyms, it will put the most probable, the synonyms that fit this context most probably first. So yeah, we'll see how to do that. And now we'll talk about language modeling a little bit. How many of you know about language modeling? Okay, all right, some people, good. So there are two approaches to language modeling: statistical language modeling and neural language modeling. We'll start with statistical one. Say we want to calculate the probability of the sentence, the patient was fading, okay? How do we do that? So we just have, and these signs at the beginning and the end are just beginning and the end of the sentence, because we have to keep track of that too. So we just have to determine how probable it is that the starts the sentence. And then the word patient goes after the at the beginning of the sentence. And then the word was goes after the patient at the beginning of the sentence, and so on and so forth, right? But you know that sentences can tend to become quite long, right? And these probabilities will just not make sense because they will never occur. Such things will never occur. So in order to simplify this chain rule, we are going to use Markov assumption. So Markov assumption says that there was this guy Markov, and he said that the future is independent of the past given the present. And this will give us what? So we will not, when we predict, when we calculate what the probability is of the next token, depending on the last string of words, we will just say that every token depends only on every next token only depends on the present token, right? So we don't care about the past, we only care about like what is now. So now is this token and the next token depends only on this one. And our chain rule will be simplified to like this, with Markov assumption, right? So we just cut the context. And here I'm using bigrams, right? So I'm using only the current token and the next token. But in reality, you can use like the window of 3, the window of 4, the window of 5, and probably not longer than the window of 5 because it doesn't, again, make much sense. Okay, so how do we calculate a single probability? Say, how do we know like how probable is the word patient out of the word the? So we just have to calculate how many times in our large corpus of the English language, like this common crawl corpus, we saw 2 words in a row, the patient, and then how many times we saw the word the, and that will give us a probability of that the word patient follows the, right? Okay, intuitive enough? Okay. There will be one problem. What if in our corpus we never saw the word fading, or like was fading, or like fading in a period? This means that, so since we are doing a product here, right, so this is a product, this means that the probability of the whole sentence will be 0, and we don't want that, right? So what do we do then? In statistical language modeling, there is a whole list of different smoothing techniques that are quite intricate that you can use in order to avoid these 0 probabilities. The simplest one, we won't go deep into them because, again, this is not the focus of the presentation. So the simplest one would be like at 1 or at k smoothing. This means that we pretend, for example, that every term that we haven't seen, we saw at least once. And this already, eliminates the zeros in our formula. Or we can do a back-off. If we're doing statistical language modeling that with, for example, a window of 4, so like every next token depends on the previous 3 words, and we haven't seen these previous these 4 words like together in the corpus, then maybe we have seen 3 words in the corpus, or maybe we saw 2 words in the corpus. So we can do this back-off, with different weights, for example, and so on. So if you're interested in that, you can find a lot of literature on different smoothing techniques for statistical language modeling. They're pretty well explained, I guess, in different resources. There are a couple of problems with statistical language modeling. One, if you have a small corpus, it will be like really bad. But that's probably with like any application that you're building. So for language modeling, statistical or not, we need a large corpus. Because if you saw a red car and if you saw blue car, you have no knowledge in your language model that purple is also a color and it's probable to see purple car. But if there wasn't any purple car in your corpus, you will just get 0 and you will have to use these smoothing techniques to somehow smooth this 0, right? Although like purple car should be much more probable. Another problem is that they don't capture long-range dependencies. As I told you, the window that you're using, it's like 2 or 3 or 4 or maybe 5 words, but scaling to larger n-grams is very, very expensive and inefficient, like people don't do that. Even if you go to one of the resources of these n-grams is Google n-grams corpus that is also available for everybody. And I linked it in the references at the end of the presentation. The larger context that Google gives you is 5 words, 5 n-grams. But that, that makes us lose some information. If we have a sentence, the patient that I met yesterday was moribund today, the word moribund, if we see it in the context with patient, we would get some higher counts. But there are like 5 words between those two, and we lose information, we will have these 0 counts all the time. The last one I already mentioned that it needs intricate smoothing techniques because, you have to implement them. One thing that you can tweak is fixing the problem of these long-range dependencies. So you can actually build n-grams at any level. We already mentioned today character n-grams, or you can do phonetic n-grams, or you can on transcription, or you can do word n-grams, or you can also do dependency n-grams. So the image that you see on the slide is a dependency tree. And dependency trees are built by dependency parsers. So a dependency parser is a tool in natural language processing that gives you the syntactic structure of the tree. And there are many libraries that you can use for syntactic parsing that are available, like Spacy or Stanford Core NLP, and I also linked them at the end of the presentation. So here, what this dependency parser gives us, so you can see words or tokens, then you can see parts of speech, and then you can see some arcs between words. So these arcs define which word governs which words, so which word modifies which word. And we can see that the main word in the sentence is the verb was, because there's no dependency going to it, okay? So that's the main one, and it's actually a tree, so it's a dependency tree. And there's a link from was to moribund, and there's also a link from was to patient. And this gives us a bigram, okay? So this is a sequence of two arcs. Then you can actually collect such statistics, again, at large corpus, and you can build a language model using dependencies now, not just word tokens. All right. Then there's also neural language modeling. I'll just touch it briefly. So the simpler example of a neural language model will be a recurrent neural network. And here what you do, you have an input layer with word embeddings, right? Then you have a hidden state, and you can see that for each hidden state, you have the previous hidden state going. So you have parameters from input to hidden, and you have parameters from hidden to hidden, right? And then at the output layer, you have to maximize the likelihood of the next word. Okay, so yeah, so you have your sentence, right? And what you do, you just maximize the likelihood that the model will predict, this word that you actually have in your sentence. How we can use this to estimate the probability of the sentence now, right? You take your new sentence, you feed it into your model, and at the output layer, it gives you the probability distribution for all of the words in your vocabulary. And you just pick the word that is in your sentence, the probability for this word, and you can again multiply it by the probability of all of the previous words that you've seen in the sentence. Okay? Great. Okay. So this is not the only type of model that you can use for neural language modeling. You can also use LSTMs or something else, anything that you want. With neural language models, you don't need any chain rules, or you don't need n-gram bases, but there are other drawbacks, like they take a longer time to train, they are much more expensive, and some of the types of models may generalize too much, because the byproduct of a language model is that you build word embeddings, and these word embeddings already know that green, for example, is a type of color like brown or white, but it doesn't, and this means that the combination of words green horse may be higher than it is in the language, just because there are other colors mentioned with horse. Yeah, in reality, so I linked, this will be at the end of the presentation, I linked a couple of language models that you can use. And in reality, actually, statistical language models are used in part with neural language models, because neural language models don't give too much improvement, and statistical language models are a bit easier to tweak if you need to change something. But then they will take you longer to implement. All right, so, and now we could re-rank all of our candidates and suggest the most fitting candidate to simplify this particular word in this particular text. Okay, let's put all the pieces together, right? So this is a little bit different from what I showed at the beginning. So we have our text, and now we know that we, in addition to token filtering, tokenization, and part of speech tagging, we can also do morphological analysis, like breaking the words into parts, into morphemes, right? To find out which word our word originally came from. We can also do lemmatization to get the base form of the verb. Then we will do feature extraction based on that and on different lexical resources and lexical semantic resources. Like we can have a resource of word frequencies, a resource of character engrams that we build, word nets, psycholinguistic database, transcriptions, and so on and so forth. So there are many resources that you can use for that. Given these features, you can build complex word identification model then that will identify potentially complex words in your text. After that, you would put them, you would use lemmas and parts of speech to do a lookup in the thesaurus and get potential candidate replacements, Then you would run these candidate replacements through your complex word identification model to filter out the ones that are too complex. then you would filter 2 simple ones, 2 grammatical ones, and rank the remaining ones with a language model. And voila, pick the first one or pick the first n ones, depending on what you want, and you have the simplified text. All right, conclusion we got here. 3 things I'd like to highlight. Linguistic knowledge gives you power. Yeah. This is number 1. Number 2, I think it's important to say it from the stage that researchers are not the final consumers of applications that we build, and we have to think about the actual users, because I have a feeling from talking to people in the community that sometimes this particular point slips. And the third one, diving into a problem gives better results than not diving into the problem. And to end this talk, I wanted to show you a slide that I stole from Minyan Khan. This was an invited speaker at the Kuling 2018 conference, and he was giving a presentation on research fast and slow. So when your machine learning model doesn't outperform, what do? So first you probably sigh, then you gather more data, maybe it needs more data to find proper weights. Then you may simplify your model, maybe it's easier just to do more hyperparameter searching. Then you go to archive and you read the latest papers that were written on the topic and so on. And then maybe number 5, you study your problem more. Okay, so I would like to encourage everyone to study your problems more and let your data speak to you. Thank you. I will share the slides, and the last 2 slides are just on libraries, resources, n-gram resources, and language models that you can use, just so, so you can find anything. Okay, I'll take any questions. Yeah.
Hello. So when you were talking about morphological analysis, I was interested, how do you deal with irregularities in morphology and language in general? What tools do you use?
So irregularities, you mean like exceptions, right? Because anything that you can describe as a pattern, you can encode as a pattern. So there are for morphological,
Sorry, there are more frequent patterns and much less frequent patterns. Right?
Yeah, so much less frequent patterns are usually something that you hard code. Yeah. Okay, sure.
You touched on it a little bit, but what was the best way to actually get a feedback loop to figure out how well?
Yeah, that's a very good question. So usually you would want to do a couple of human evaluations, and for at Grammarly specifically, we have a separate tool for feedback analysis that gives us information whether the user accepted or ignored what we suggested, and we can reiterate on that all the time. Yeah. Okay. Any other questions? I hope it wasn't too complex or too simple.
Right, well, let's just like to thank Mariana again.